In this video, we will focus on the coefficients of lift and drag. We will also focus on reference area, which is essential to correctly calculating and predicting the lift and drag forces on objects of interest. Let's get started by reviewing lift and drag. Lift forces act normal to the upstream flow and can be calculated by taking the product of 0.5, fluid density, upstream velocity squared, the reference area, and the lift coefficient. Drag forces act parallel to the upstream flow and can be calculated by taking the product of 0.5, fluid density, upstream velocity squared, the reference area, and the drag coefficient. Lift and drag forces act on the center of pressure of an object and give rise to a resultant force. So we now know that a body interacts with a surrounding fluid through pressure and shear stresses. However, the lift and drag on bodies immersed in fluids have numerous complex dependencies, such as inclination, shape, viscosity, and compressibility. Let's take this car. We can obtain the lift and drag forces on this car by integrating the effect of shear stresses and pressure distributions on its surface. You would need the equations shown here. And here, you can see the pressure and shear forces on a small element of the surface of the car. You would need to carry out the calculations on this small element on the car's surface. To carry out the integrations for lift and drag force for the entire car, we must now know the shape of the entire car. We would then need to know how theta changes as a function of location along the surface of the car, as well as the distributions of pressure and shear stresses at each location. This is not easy. As a matter of fact, knowing how theta, pressure stress, and shear stress vary along the car is extremely difficult and time-consuming. This is why the lift and drag coefficients are so important. Aerodynamicists use these coefficients to model the complex dependencies on lift and drag of objects. Here, you see the lift and drag equations rearranged to enable the calculation of lift and drag. What's great is that the lift and drag coefficients can be determined experimentally. Imagine setting up an experiment where you can control the density and velocity of a fluid, such as in a wind tunnel. If you could have devices that can measure lift and drag forces, then you can determine the lift and drag coefficients of the object. Here's an example of a car in a wind tunnel. The minimization of drag forces on a car such as this one is important. Here's an example of a skier in a wind tunnel that is holding a posture that is meant to minimize drag in high-speed skiing. This slide was discussed in the video on drag. We now revisit it here. These drag coefficients were determined by fixing the density and velocity of the fluid, which in this case is air, knowing the reference area, and measuring the drag force. Once you determine the coefficients, you can then use the lift and drag equations to predict the lift and drag forces on an object over a range of relevant flow velocities. No integrations are needed. This method's a lot simpler than carrying out integrations that require you to know how theta, pressure stress, and shear stress vary along an object. However, you have to be very careful about the reference area that you use in your calculations of lift and drag. What is a relevant reference area? So, here's the important thing about reference area. In principle, the reference area is arbitrary. You should choose an area that is characteristic to what you are considering. Let's take this object in this figure. It is a wing with a chord length c, maximum thickness t, and span L. If you need to calculate the drag force or drag coefficient on this wing, you should consider the frontal area of this object. The frontal area can be calculated by multiplying the thickness of the wing t by the span L. If this wing is moving horizontally, this frontal area is the area that the incoming flow encounters, and therefore should be used in the calculation of drag forces. Therefore, in this case, you replace A in the coefficient of drag equation with T times L. Let's suppose that you are interested in calculating the drag coefficient of an underwater vehicle, such as a submarine. In this case, you will need to calculate the area of the front of the submarine and use that area in your drag coefficient equation. Let's suppose that you are interested in calculating the drag of a bus. In this case, you will need to calculate the area of the front of the bus and use that area in your coefficient of drag equation. Now, if we want to calculate the lift generated by this wing, we have to use a different reference area. In this case, the relevant area in the generation of lift is the planform area. The planform area can be calculated by multiplying the chord length of the wing C by the span L. Therefore, you replace A in the coefficient of lift equation with C times L. If you'd like to calculate the lift of the wing shown in this picture, you would need to determine its planform area and use that as your reference area. So now let's summarize the concepts on reference area that you have just learned by looking at this P-51 Mustang. Here's a picture of it in flight. The airplane generates a drag force while it is moving. If you need to calculate the drag force of the P-51 while it is in level flight, you would need to know the frontal area of the aircraft and use this as the reference area in your drag coefficient equation. If you need to calculate the lift force, or the coefficient of lift, generated by the P-51 while it is in level flight, you would need to know this area of the aircraft and use it as the reference area. This video focused on the drag and lift coefficients. These coefficients can be determined experimentally and enable the lift and drag forces of an object to be determined without having to carry out complex integrations. However, correct calculations of lift and drag depend on using the appropriate reference area. Frontal area is typically used for the calculation of the drag coefficient and drag force, while the area that is relevant to the generation of lift is used for the calculation of lift coefficient and lift force. Be very careful when choosing your reference area. Now let's take a quiz. Here we have a wedge that is oriented to an oncoming flow of air in the manner shown here. The wedge has a width of 3 meters, a length of 5 meters, and a height of 4 meters. Width, length, and height are defined here. What is the reference area that should be used to calculate the object's drag coefficient? Please pause the video now, work out the problem, and select one of the choices to the left. Unpause the video to see the solution to this problem. The correct answer is 12 square meters. Here's why. Imagine that you are a particle flowing with the air, and you are being propelled towards the wedge. The reference area that you would be seeing would be rectangular, with a height of 4 meters and a width of 3 meters. This is the area that you would use in your calculations of drag coefficient.